Hi there, my name is Andrew Brown, and welcome to Stereoisomers. This video will survey the main classes of stereoisomers you can expect to see in the MCAT. We'll start with the conformational isomers, making sure to review Newman projections as a tool for characterizing them. Cyclic conformers won't get quite as much airtime, but we'll be sure to examine a notable example of isomerization in cyclohexane. A review of chirality will set the stage for our exploration of enantiomers, diastereomers, and cis-trans isomers, and we'll finish up with meso compounds. After watching this video, you should be able to answer questions like this one, which asks you to classify a pair of potential isomers. Many of the isomers you will see in this video are, at best, subtly differentiated. Therefore, it is most clear if we start with one of the more general classes of isomers, conformational, and work our way up to the more particular ones. Presented first for you here is the definition of conformational isomers. It's always best with isomers, however, to use example molecules to see what's going on. If we follow the methyl group in 1-bromopropane, rotation of a single bond should flip the methyl group upside down. That's all it takes to produce a conformational isomer, and the pair of isomers together are referred to as conformers. Before jumping directly into our next class of isomer, we'll turn to Newman projections briefly now because of their usefulness with conformational isomers. A Newman projection is basically just the sideways view of a molecule along one of its bonds. They allow you to visualize the groups attached to each end of the bond and characterize the effect of bond rotation. One of the ramifications of bond rotation is the interplay between the substituents on either side of our bond being examined. Let's review the names of each of the noteworthy conformations. Anti-staggered is the most favorable, with the bulkiest substituents farthest away from one another, separated by 180 degrees. The next conformation, eclipsed, is relatively unfavorable because of steric hindrance between the aligned substituents. The favorability of the gauche conformation is in between those of anti-staggered and eclipsed. Even though its rear methyl group is near the bromine atom, at least they are not in line, as in the eclipsed conformation. Speaking of which, as you may have recognized, there exist multiple different renditions of the eclipsed conformation, one for each substituent on the front carbon. Therefore, we distinguish the totally eclipsed conformation, the one where the bulkiest substituents in the front and back are aligned, as being the least favorable overall. Notice at the bottom of the screen, the molecules on the left and right are the two conformers we saw in the previous section. Based on what we have just learned about Newman projections, you can now see why certain conformational isomers are more common than others. Okay, so now that we've covered linear conformations, we should introduce their cyclic counterparts. With cyclic conformers, the main element affecting stability is ring strain. Although it is perhaps a bit out of the scope of the MCAT, the ideal bond angle between sp3 hybridized atoms in a molecule is defined as 109.5 degrees. The farther away from that angle a bond is, the less stable the bond, and the more ring strain in the compound. Therefore, cyclobutane, which is shown in its puckered orientation here, contains the most ring strain out of the cyclic compounds you will see. There is actually an even smaller ring possible, cyclopropane, but the ring strain in that molecule is so great that it exists only transiently. Take a look now at cyclopentane. It is pictured in the envelope conformation, where 4 of the 5 carbons are in a single plane, and the 5th is either above or below, alleviating a little bit of ring strain. Now we'll introduce cyclohexane. Because it is such a key reactant in organic chemistry, you will want to be familiar with its 3 most common conformations: the boat, the twist boat, and the chair. They are actually depicted here in order from most to least ring strain. That means that the chair is cyclohexane's most stable conformation, and the boat is its least stable conformation. We'll see why in just a moment. In addition to ring strain, steric hindrance between substituents also produces something called flagpole strain. Remember that substituents attached to a cyclohexane frame can either be in the equatorial or axial position. In 3-chlorocyclohexanol here, the hydroxyl and chlorine groups on carbons 1 and 3 are both in the axial orientation. Just as we saw with Newman projections, when bulky substituents are too close to one another, steric hindrance arises. However, cyclohexane is special. When there is too much flagpole strain, cyclohexane can undergo a ring flip, in which the whole molecule inverts, switching all of its axial substituents to equatorial and vice versa. Ideally, bulky substituents prefer to be in the equatorial orientation, where they point outward from the cyclic compound and do not really interact with each other. Okay, so that's enough on conformational isomers. Now, as we move on to the enantiomers and diastereomers, let's first make sure that we have a solid understanding of chirality. At the most basic level, chirality refers to two objects that are mirror images of one another. A rather accessible example of this is your hands. If you imagine a plane of symmetry drawn between them, it appears as if your right hand is a reflection of your left, so each of your hands is said to be chiral. A chiral organic molecule, then, is denoted by a chiral carbon, one that is bound to 4 unique substituents, just as with your hand and fingers. Having 4 different substituents means that the chiral carbon is a stereocenter that will be distinct from any angle. Thus, the chiral molecule itself cannot be manipulated into its mirror image unless bonds are broken. That is the case with 1-chloroethanol, and so we'll hang on to it for the next class of isomers. Enantiomers are a type of configurational isomer, those that are defined by fundamentally different bonding between atoms that also happen to be non-superimposable mirror images of one another. 1-chloroethanol is such a great example here because it shows that enantiomers' inability to be superimposed on one another depends on their chiral carbons. Remember, chiral objects cannot be converted into their mirror images by simple bond rotation, and neither can enantiomers. When you can convert a molecule into its mirror image by rotating the carbon-carbon bond, then they're either the same compound or weren't chiral to begin with. Only if the two molecules are non-superimposable mirror images, and thus different compounds, can they be considered enantiomers. Diastereomers are another type of configurational isomer that contain multiple stereocenters and are not mirror images of one another. Instead of trying to describe diastereomers in words, however, it's better to look at an example of some. By the formula 2 to the n, we can predict that 3-bromobutan-2-ol with its 2 stereocenters will have 4 potential stereoisomers. Notice here, in the diastereomers, only one of the 2 stereocenters is mirrored. Also notice, though, that by rearranging the stereocenters, we have also generated enantiomers. This illustrates nicely the close relationship between enantiomers and diastereomers, and reminds you to exercise caution when identifying either type in molecules with multiple stereocenters. You're probably wondering by now what happens when you introduce double bonds or rings, and that's where cis and trans isomers come in. Just as with the rest of configurational isomers, cis-trans isomers are not interconvertible. Before, it was because of stereocenters within the molecule. Now it is mainly because of double bonds and rings. To quickly review cis and trans, in cis-3-methylbut-1-enol, the hydroxyl and propyl groups are on the same side of the double bond. In trans-3-methylbut-1-enol, however, notice that the propyl substituent has been switched to the other side of the double bond. Now it is on the opposite side of the double bond from the hydroxyl group, which defines the trans arrangement. Now, although we typically think of cis and trans as describing double bonds, there are actually some examples where only single bonds are involved. Take cis-2-ethylcyclopropanol, where the hydroxyl group and the ethyl group are both in the same three-dimensional orientation. There is no double bond, but the carbon atoms in the pentane ring are somewhat restricted, so the stereocenters do not freely rotate. In trans-2-ethylcyclopropanol, it is the same concept, only the hydroxyl group is now pointing into the screen and the ethyl group pointing out of it. There's still one important type of isomer left to explore, the meso compound. Meso compounds contain chiral carbons, just like enantiomers and diastereomers, but also display an internal plane of symmetry. The internal plane of symmetry means that any optical activity from one of the stereocenters will be neutralized by the other stereocenter, producing zero net optical rotation. For a molecule such as 2,3-dibromobutane, rotating stereocenters can produce enantiomers or meso compounds. A good rule of thumb is that the meso compounds will have the same substituents on each of its chiral centers, and they will mirror one another across an imaginary plane of symmetry. Enantiomers might also involve the same substituents on each chiral center, but in different configurations. Okay, so that does it for the material this video is going to review. Now, practice what you've learned with some sample questions. This first one is asking you to categorize a pair of isomers. The answer should be B. If you look at the answer choices, you'll notice that most of them depend on stereochemistry to one degree or another. Meso compounds don't, but we can quickly eliminate that answer here because there are no obvious planes of symmetry within either molecule. So if the answer is diastereomers, enantiomers, or cis-trans isomers, we should first characterize any stereocenters in these compounds. There happens to be only one in each molecule, so diastereomers are also out. We probably have enough information to just pick enantiomers at this point, but let's continue the explanation to make sure. Examining each of the stereocenters reveals that the CH2 and H groups are in the opposite orientation between isomers. Thus, as long as there are no stereocenters in the rest of the molecule, the two compounds are enantiomers. And now another practice question. This time, you're given two compounds and are just being asked to identify the type of stereoisomer pair present. The answer should be D. As we said before, stereoisomers are defined largely by their stereocenters, and so that's a good place to start. Each molecule contains two stereocenters in this case. Next, imagine you're looking down the central carbon-carbon bond, the one that is closest to the dashed line bromine in the molecule on the left. We've provided the corresponding Newman projection here. Now, do the same with the molecule on the right. Uh-oh, look at the Newman projections. They're the same. That means we're not dealing with two compounds at all here, but rather one from two different angles. If we rotate the central carbon-carbon bond now, watch what happens. It's perhaps not as obvious in the Newman projection, so look at the wedge dash diagram. Notice the internal plane of symmetry that emerges. This must be a meso compound. All right, if you got those two questions correct, great job. If not, please feel free to watch this video again as many times as you need. Before we finish, let's take a few moments to review what was covered in this video. Everything you saw in this video was a stereoisomer. However, even within stereoisomers, there are meaningful differences between categories. We started with the conformational isomers, those that could be interconverted simply through bond rotation. If the breaking of bonds was required to interconvert, that indicated configurational isomers. Configurational isomers that were non-superimposable mirror images were defined as enantiomers. Differences across a double bond or because of a ring were attributed to cis-trans isomers. In the absence of an internal plane of symmetry, configurational isomers with more than one stereocenter that were non-superimposable and were not mirror images of one another were defined as diastereomers. If a configurational isomer with multiple stereocenters did have an internal plane of symmetry, we saw how it could be a meso compound. Thanks very much for watching, and good luck in your continued MCAT study.